Hi everybody, this is Dr. Kirkvold, Engineering 314, Mechanics and Materials. We are finally off to the races with Chapter 3, Crystalline Solids. We started this particular chapter in class in lab about a month and a half ago now, and I'm going to go ahead and start again from the beginning just so we have a refresher. Okay. In this chapter, and by the end of this lecture, you should be able to describe the difference in atomic arrangement between crystalline and non-crystalline solids. You should be able to identify the features of a material's atomic structure that determine its density. And you should be able to describe the various circumstances under which a material property varies with the measurement direction. So all of those particular topics, pieces of information, and the definitions of them are fair game. You know, we've talked about how all these materials, and particularly for crystals, are made up of atoms, and it matters how those atoms are arranged with each other. When the atoms, shown here as a blue sphere, have random packing, in other words, they're not in order, and you have various amounts of space between each of the atoms and in different arrangements. This provides a pretty non-dense or a low density form of this material as a composite whole. That's different than an ordered packing system, which is much more dense, less space in between the atoms, and it's a repeated pattern. All right, so we're going to talk about these repeated patterns as crystalline materials. Example here is crystalline silicon dioxide. The atoms pack in periodic 3D arrays. This is pretty typical of metals. Many of our ceramics, some polymers, though they function in a slightly different way. We'll get to that in the polymer chapter. Specifically, this is different than you could take those same atoms, the silica and the oxygen, and you could arrange them in a non-crystalline form where it's random bonding. The atoms don't have periodic packing, and this occurs if you have very complex structures or rapid cooling conditions. We would call this non-crystalline state amorphous. Okay, there's your silicon dioxide, the most abundant material on Earth. All right, so how can I stack my metal atoms to minimize the space? Right, we've looked at that. There are different ways you can stack these atoms on top of each other. To start with a 2D version of it, we could arrange the atoms on a piece of paper or in a box in different ways. Here are two of the options for arranging one layer of these atoms. On the left, you have them nestled into each other in a very tight fashion, and on the right, they are much less ordered. I mean, not ordered, but they're much less densely packed. Okay, so what does this look like in 3 dimensions? We have to take these different layers and stack them. You could take the pattern on the right-hand side, for example, and put the second layer directly on top of that first layer. However, could you not also shift the entire layer, second layer, over about a half of an atom and down about a half of an atom, and then each atom would nestle down into, let's see if I can get my laser pointer, each atom would nestle down into the space between it. Metals tend to have some of the most simple crystal structures that exist. They're densely packed, usually high atomic mass. We're going to go ahead and look at 3 of these such structures to learn how to define crystals themselves. We'll start with the most simple structure. And in order to build our model, we need to start with our atom. Atoms are modeled as a sphere with a radius r. We can calculate the atom's volume. Volume of the sphere, 4/3 pi r cubed. But what about the spatial arrangement of the atoms? We need at least 4 pieces of information in order to be able to fully define the structure itself. So we're going to go back to our 2D model and start with one layer of atoms. This 2D crystal on the left represents one spatial arrangement these atoms have for each other. As we move over into the 3D crystal structure, you would stack them on top of each other. In this form, we have stacked the atoms directly on top of each other. In order to define this structure, we use what's called a unit cell. This contains all the information required to fully define the crystal structure, and we don't need to go ahead and define every atom. We're picking a portion of this structure, this crystal, and we're going to define it in such a way that it is repeated throughout the material. How might we represent this structure? What is the smallest cutout of the structure that contains all this information? What is this unit cell? We could answer one atom, but that's not going to tell us about the arrangement. If we choose a square, like the 2D on the left, the red square, or the cube on the right, then we have all the information embedded within this particular structure, within this unit cell. Now we can start to quantify the model. Using the same three-dimensional configuration that we used on the previous slide, we can visualize this model 3 different ways. First of all, let's let the atoms remain the spheres, just like we said, and assume that they are solid spheres. We use this model to define our first term, the close packed direction. The close packed direction is the line of intersection where atoms touch each other. So we ask ourselves, where in this model are the atoms touching? They are touching along the cubed edges, and so these cubed edges represent the close packed directions. Secondly, we visualize the same model by representing the atoms as smaller spheres. We can see through the structure this way, and finally, when we repeat this structure and expand it out like a real structure would be, we can notice that our initial red atom that we have been looking at is identified. When we isolate the red atom and its touching nearest neighbors, we can see spatially how they are oriented with respect to each other. So we're going to define the coordination number as being the number of nearest neighbors. How many nearest neighbors does the red atom have? 6, top, bottom, and each of the sides of the cube, so that the coordination number is 6. Do you remember when I said we were going to need 4 pieces of information to fully define our model? Well, here's where we start to need 3 of the pieces of information. We're going to define the atomic packing factor, or APF, as a unitless number less than 1 that represents the proportion of atomic material, the volume of that material within the unit cell. So the APF is the volume of atoms in the unit cell, and we divide this value by the volume of the unit cell itself. In order to calculate the APF, we need these 3 pieces of information, which are represented in the colors here at the bottom. We need the number of atoms per unit cell, we need the volume of one atom, and we need the volume of the unit cell itself. Our problem statement is to find or calculate the numerical value of the atomic packing factor for a simple cubic structure. The unit cell is shown below, and we will define the edge length for this cell, or any unit cell, to be the letter A. In order to determine the three terms needed to calculate the atomic packing factor, we need to know the volume of the unit cell in terms of A. We need to know the relationship between the atom's radius r and this value of A. So our first question, what's the volume of the unit cell in terms of A? Since the unit cell edge is always of length A, that is pretty easy. Our volume will always be A cubed, no matter which structure we're looking at. And secondly, what is the relationship between the atom radius r and A? Well, here, one edge of our cube has two atom radii within it. That's our close packed direction. Therefore, A, the edge of the cell, is equal to 2r, or r equals half times A. Once we know the relationship between A and R, we can calculate the atomic packing factor. We can count the number of atoms in the cell. Here, this unit cell contains 8 corners, and there is 1/8 of an atom in each of those 8 corners. So 1/8 times 8 is 1 atom for the whole unit cell. You can see that value we inserted up into the green box. Second, we know the volume of a sphere is 4/3 pi r cubed. As we substitute in the relationship for radius in terms of A, we get the value we see here. And finally, we know that the volume of the unit cell is always A cubed. Solving this expression, we get that the atomic packing factor is 0.52 for a simple cubic structure. What does this mean? Well, we've fully defined our structure and our model. I guess I see it in two ways. 52% of the volume of this unit cell is material, atom material, or you could say 48% of the volume of this unit cell is not atom material. Now that we have fully defined the simple cubic structure, let's look at our second structure, the body-centered cubic BCC structure. This structure is different from the simple cubic structure because, as you can see, there's one atom that has been inserted into the center of the unit cell, into the center of what would be a simple cubic structure, pushing the corner atoms outward. Atoms touch each other along the cubic diagonals. Using the same methods that we used for the simple cubic structure, we see that the coordination number for the body-centered cubic is 8 because the 8 corner atoms are the nearest touching neighbors for the center atom. There are now 2 atoms per unit cell because we have the initial 8 1/8 atoms, just like for the simple cubic structure, but now we have also the one additional full atom in the middle. For this structure, where are the close packed directions? This time the edge atoms are not touching, but the atoms do touch along the cube cross diagonal. We follow the same concept. The length of the cross diagonal close packed direction can be solved for using a cross section of the cross diagonal. We use the Pythagorean theorem and can calculate the length to be the square root of 3a. So everything we have the length of the cross diagonal close packed direction can be solved easily using a 2D cross section of the cross diagonal. Because there are 4 radii along the close packed direction, and one side of the cube is length A, we can solve for the length of the close packed direction using the Pythagorean theorem and establish the relationship between A and R. So now we have everything to calculate the APF. There are 2 atoms in the cell. The volume of the atoms is 4/3 pi r cubed, inserting r as a function of A. And the volume of the cell is always A cubed. Therefore, the atomic packing factor for a body-centered cubic is 0.68. Our third structure is the face-centered cubic structure. The face-centered cubic structure has an atom centered on the face of each side of the unit cell. This gives us 4 atoms per cell, the 8 1/8ths in the corners, and now 6 half atoms, one on each face. The atoms touch each other along the face diagonal, and we have a coordination number of 12. Face diagonal length, we get the square root of 2a, and that equals 4 atomic radii. Again, now we have everything we need to calculate the atomic packing factor. The atomic packing factor for a face-centered cubic structure is 0.74. This is the highest APF possible. Earlier I said I would go through the calculations to fully define the models for 3 unit cells that were cubic, and I would show you one additional non-cubic unit cell. Here is the example of a non-cubic structure called the hexagonal close packed direction. You'll notice that the top and the bottom layer of this particular unit cell has the atoms arranged in a hexagonal form. The second layer, the B layer, sandwiched in between, nestles down in between each of the other 2 top and bottom layers. We have a coordination number of 12. There are 6 atoms in this unit cell. The atomic packing factor is also 0.74. Using these models, we can calculate the theoretical density of a material. If we know its structure, we can calculate its density. The density is going to be the mass of the atoms in the unit cell divided by the total volume of the unit cell. Here we know that N is the number of atoms in the unit cell, where A is the atomic weight. The volume of the unit cell is the A cubed, just the same as we've always had, and capital N sub A is Avogadro's number. Here's an example. The question is find the theoretical density of chromium. So our solution, if we know that chromium is a body-centered cubic structure, we know that the atomic mass is 52 grams per mole, the atomic radius is 0.125 nanometers, we have 2 atoms per unit cell, and A equals 4R divided by 3, square root of 3, and that equals 0.2887 nanometers. Inserting all of these into the equation for the theoretical density, we end up getting 7.18 grams per cubic centimeter, and when you measure the density of this particular material, generally it becomes, the value is 7.19 grams per centimeter. Notice that these are not the same values. So why might there be some difference between the theoretical density and the actual measured density? There's probably many reasons, but I can think of at least 3 offhand. First of all, the variation in the precision of the measurement equipment is never going to be precise. It's likely not a 100% pure material. There's some contamination somewhere, and the density will be affected by that contamination. And finally, the crystal structure itself, because it's a polycrystal, is not going to be perfect. Anytime there's a disruption to the crystal lattice work, this will reduce the density of the material. We can use density to help develop general characteristics for different material classes. In general, the density of metals is going to be higher than that of ceramics and that of polymers. Why might this be? Well, there's various reasons, usually looking at the packing structure, the atoms themselves, and the type of bonding. Metals have close packed metallic bonding. They also are often atoms of larger mass, atomic mass. Ceramics often have lighter elements and are of less dense packing structures. Polymers usually have the lowest packing density. They're usually amorphous or only partially crystalline, and they're made of some of the lightest elements, the carbon, hydrogen, and oxygen. Composites will have intermediate values. Crystalline materials, such as metals, can be either single crystals or they can be polycrystalline, or having many crystals within them. There are some engineering applications that require single crystals. For example, a diamond, single crystals are used for abrasives. Those abrasives are usually grown in the lab and are not natural diamonds. Properties of the crystalline materials are often related to the crystal structure itself. So, for example, quartz is going to fracture along the crystal planes because some of the planes have weaker bonds than others. Most engineering materials are polycrystals. In the image here, each grain that you see is a single crystal. In the areas where the grains are randomly oriented, then the overall component properties are not directional. We call this isotropic, meaning the properties are the same in all the directions. Grain sizes typically range from 1 nanometer to 2 centimeters. The areas where the grains are not randomly oriented, as shown in the middle of this image, the properties are going to be anisotropic, meaning they will be very directionally oriented. It is not the same in every direction. So what's the difference in the behavior of single crystals versus polycrystals? For single crystals, we know that the properties are going to vary with the direction of testing. The behavior will be anisotropic. It can't be isotropic. An example is a single crystal of iron in a body-centered cubic formation can be tested in, as shown, these two different directions. And when that is the case, it will have a weaker or a smaller modulus elasticity in one direction than another. Polycrystals might be anisotropic, and they can also be isotropic. Okay, it can go either way. You'll see in the image below, these are crystals of a steel, and on average, they're approximately the same size. They are randomly oriented. There's not one different direction to it, and these grains are generally textured, meaning the sides are not perfectly smooth. If that's the case, then the material is generally considered anisotropic. Some metals, as well as nonmetals, have more than one crystal structure possible. This is a phenomenon called polymorphism. When it's found in elemental solids, the condition is sometimes called allotropy. The prevailing structure depends on both the temperature and the external pressure. One familiar example is carbon. Graphite is the stable polymorph at ambient conditions, whereas diamond is formed at extremely high pressures. Because there are so many different possible crystal structures, it's sometimes convenient to divide them into groups. One of the ways that we can do this is to look at the unit cell geometry. Within this framework, an XYZ coordinate system is established with its origin at one of the unit cell corners. Each of the X, Y, and Z coordinates coincides with one of the three edges. The unit cell geometry is completely defined in terms of 6 parameters: the 3 lengths of the edges, A, B, and C, and the 3 interaxial angles, alpha, beta, and gamma. You can see them shown here in this figure. These are sometimes called the lattice parameters or lattice constants. There are 7 possible permutations of these constants that result in the possible crystalline systems. If you take a look at table 3.2 in your textbook, you'll see the lattice parameter relationships and the figures that show the different unit cell geometries for 7 different crystalline systems. Sometimes it's necessary to specify a lattice position within a unit cell. These positions can be defined in terms of 3 different lattice position coordinates, which are associated with the X, Y, and Z axes. The coordinate specifications are possible using 3-point indices, which are fractional multiples of the unit cell lengths. Here I've shown a unit cell with edge length equal to 1, A, B, and C representing the edge length in each of the 3 different directions. And the point coordinates for any position in the cell correspond to the X, Y, and Z point values between 0 and 1. These can be scaled up or down to represent the crystal structure. Please review examples 3.5 and 3.6 in your text. And finally, we can define linear density for a given unit cell as the value of the number of atoms per length of the close packed direction vector. In other words, the linear density of the atoms is the number of atoms, or the diameters, along the close packed direction per unit length of that direction vector in terms of A. For example, when you calculate this one, the aluminum in the 110 direction, we have a unit cell A value of 0.405 nanometers. You can calculate the linear density of this material to be 3.5 per nanometer. To summarize, we've covered a lot of material. We've introduced many new terms and concepts, such as how atoms can be assembled into crystalline or amorphous structures. We've talked about face-centered cubic, body-centered cubic, and simple cubic structures. We define those using coordination number, atomic packing factor. We have this close packed direction that we had. We know that there exists other forms such as the hexagonal close packed direction or structure, and that the simple cubic structure is pretty rare. We learned how to predict the density of a material given the atomic weight, radius, and the crystal geometry. We also know that materials can be either single crystals or polycrystalline. We know that material properties vary within a single crystal orientation. If it's a single crystal, they're generally anisotropic. They're different in different directions, but for polycrystalline materials, the grains are usually randomly oriented and the properties are usually isotropic or non-directional in nature. Some materials have more than one crystal structure. This is referred to as polymorphism or allotropy. And finally, the crystal systems are defined by a unit cell for which we can calculate a linear density. And with that, we will wrap up the chapter 3. Please look at your homework, look at the examples. This slideshow is not intended to be a replacement for reading your text. Please do the homework problems and ask me any questions if you have them. Thanks.